session. Okay, and then we have another example this way. Your box is here, a force is applied this way. As usual, you have to resolve it into its Fx and Fy. If it's not clear to you, extend it. If it's clear to you, then just resolve it. So this gives me a positive Fx and a negative Fy. So we are only concerned with the parallel component to displacement, which is Fx. So Fx is in the same direction as your delta x, so that gives you a positive work done. And the same example here, if you can't see where it should be resolved, extend it. This is your F, resolve it, Fx, negative Fy. As usual, parallel components only, so Fx is in the same direction as x, so that gives you a positive work done. This is the example for negative work done. So here, resolving it here, we get a negative, we get a Fx in the left, but our displacement is to the right. We are assuming our displacement is to the right, so that gives us a negative work done. Same thing here, resolving it here. Fx is in the opposite direction, negative work done. F is in the opposite direction, negative work done. Same thing here, extend it. This is your F. This is your Fy. This is your Fx. So Fx is opposite direction. Same thing here. Extend it if you can't see it. So this is your F, Fx, Fy. Okay. So always try to extend it if you can't see how to resolve it. That should give you your direction with respect to your displacement. All right. So I don't remember if we have talked about this piano example. Let's just do it again. So assuming that I am pushing, so this is a man pushing the piano up the plane, okay? So he's pushing the plane and he's applying a certain amount of force. For example, he's applying an F of 40 newtons, right? And this is my F and this is the weight of the piano. The F is F external pushed by me. Weight is from the piano, that's the weight of the piano. Now the displacement is upwards. Let's say delta x is upwards. My F that I applied is in the same direction as displacement, so I am doing positive work. The force that I'm pushing is in the same direction as displacement. I am doing positive work. However, the weight, the force of gravity is doing negative work. Why? If I were to resolve this, so this is my W in the X direction. Alah, tak nampak. Okay, so this is my weight and I resolve it. This is my weight in the X direction and this is my weight in the Y direction. And my weight in the X direction, we are only concerned about the parallel component. So WY is no longer, we're not considering it lah. So we are looking only at the parallel component to displacement, which is WX. But WX is in the opposite direction as displacement. So work done, okay, so what I can say is work done by gravity is negative. Okay, work done by gravity is negative because Fg is this way, okay, force of gravity, but we call it weight most of the time. But work done by external force is positive. By external force, you can just say capital F is positive. Okay, sorry for the bad handwriting. Okay, so I hope that's clear. So what if the box moved downwards? The opposite situation will happen. We are applying force upwards, but the box decides to keep sliding down because it's too heavy. We are not applying enough force. So when that happens, displacement is in the opposite direction as applied force. So we are actually doing negative work. We are wasting our energy because we are doing negative work. So the box is not moved in the positive direction. So this is my F. Displacement is this way. So now F external is doing negative work, right? So that's your first situation. And same thing, resolve your weight. It's this way, Wx, Wy. This is your W. So Wx is in the same direction as your delta x. Cool. So now we have force of gravity is doing positive work. So gravity happy lah. Okay, so that is it. Any questions for me so far? Okay tak? Okay je kan? It's an easy concept. In the same direction, positive. In the opposite direction, negative work. Okay, so work done by multiple forces. So here we have a box and we have reaction force, we have a pulling force, we have the friction force, and we have weight. Can anyone tell me what is what is the force that is relevant to work done here? So here we have displacement going to the right. What is the force that is relevant to work done? Anyone wants to answer me?
P and F.
No? Apa dia? I heard someone trying to answer. Tak ada? Tak ingat dah? Berapa hari? Okay. P, okay. Is friction relevant or not?
Relevant to
Because
F is
negative work done.
opposite direction from the displacement.
direction. So any force that is parallel to displacement is relevant to work done. If it's perpendicular, it's just going to give you 0. So what are the forces? Thank you. What are the forces that is perpendicular? This guy is perpendicular. It's a buat tik pula. It's a bad force. So reaction is perpendicular, so it's going to be 0. Weight is perpendicular to displacement. It's going to give me a 0. So here, the dot product of mg with displacement will be 0. The dot product of reaction force with displacement will be 0. So work done, the total work done is just the force, the pulling force, and also the friction. Okay. Nanti kita buat example. Don't worry, that's just this equation, just explaining you the concept. So here, when they add all the forces together and they found the dot product, it's actually F net. It's actually F net, and F net dot product with D is F net cosine theta D. You can also use this equation to solve for it if they ask you for total work done. If they ask you what is the work done by gravity, what is the work done by the pulling force? So you can't use this F net equation. You have to do it separately. Nanti kita buat example. Okay, questions to ask when solving problems. What are the forces? Okay, we already done this. We have reaction, we have friction, we have weight, we have external force, and in which direction is the net force? You already learned this in chapter 3. Finding the net force should be easy by now. And F net will give you the work done, the total work done when you times it with displacement. Remember, only parallel components is relevant. Even though your F net has something in the X, something in the Y, only your Fx is relevant to work done because we want parallel components. Ingat F net ada direction kan? Ada Y, ada X, but only the parallel is relevant to work done. So that is why the cosine is there. Okay, so the force on an object may not always be constant. So previously we talked about F equals to 20 Newton, F equals to 10 Newton. It doesn't change. It doesn't change with time. We are applying constant force. So now it's asking you what happens when the force is varying. So when we have a varying force, for example, elastic force of a spring. So why is it varying? It looks like constant to me. No, it's not actually constant. For example, if you move your box by 1 centimeter, the force is different. And if you move your box by 10 centimeter, the force is different, right? So that is what it means when the force keeps on changing. There are certain forces that keeps on changing with a certain condition. And one of it is elastic force. Okay, so I don't know if we learned about this yet. or not? Oh, belum. Kita tak belajar lagi pasal ni. So F equals to minus Kx, where X is the displacement of the spring from original position. Okay, and this guy is your spring constant. Spring constant is a constant value. Ambil kau banyak gila arrow. Constant value. Okay, jangan nak mandai vary kan K pula. K is constant. X berubah mengikut kita compress banyak mana, kita stretch banyak mana. The force changes with X. The force changes with whatever X that is the spring is experiencing lah. So F is minus Kx. What does it mean? It means that a negative force is produced with the displacement. Okay, contoh So this is me. As usual, I am always the subject of an example. So this is me. Okay, sorry, tadi spring that wasn't me. Why did I say that was me? Okay, this is me wearing a skirt today. Lepas tu, I decide to push my spring. Okay, at first, my spring was here. So this is X equals to 0, my initial position, no displacement at all. Original position is 0 displacement, right? Okay, so I decide to push my spring or compress it. When I try to compress it, I'm pushing it with a force, right? Okay, I am pushing it with a force. So this is me applying F equals to F applied lah. I will call the pushing force as F applied by 20 newtons. Okay, that is F applied. Okay, trying to break this down to make it easier. Okay, so when I try to compress it, it obviously becomes smaller, right? So now it's compressed. So now this is the final position. This is Xi. This is XF. XF is, let's say, 10 centimeters. So now you have delta X of 10 centimeter. How do you find it? XF minus XI. Delta always refer to final minus initial. So delta X is 10 centimeter now. Okay, so, but this is F applied. This is elastic force. It's not the same thing. So what is F equals to minus Kx? It is the force that opposes whatever change that I'm trying to do. Okay, force ni pula. Spring ni alive. Cuba korang perasan, cuba korang imagine if you try to stretch a spring, it will want to go the other way. It wants to go back to its original position. If you try to stretch it, it's very hard to stretch it. So it wants to go back to its original position. And when you compress it, it wants to go back to its original position, right? It's pushing you back. It's pushing, when you are compressing it, it wants to membesar. When you are trying to stretch it, it wants to mengecil. Betul tak? When you do that to a spring. So that is elastic force. It is trying to oppose whatever displacement. So that is why we have a negative in our equation. It is a opposing force. Opposing. Okay, always trying to oppose whatever that is done to it. So this is the elastic force and this is applied force. It's two different things. Okay, I hope you are clear with this. F by spring is here. I am pushing it. F spring decides to push back. It's alive. If I am stretching it this way, this is F applied. F elastic force is this way. Okay, by Newton's third law, it should be equal and opposite, right? Newton's third law says the force should be equal and opposite. So this is what is happening. FEF will be equal to F applied, but in the opposite direction. Okay, so that was like a brief intro. Kita adalah brief sangat. That was an intro on spring lah, because you will look at spring later on in this chapter. Okay, so one of the example is F equals to minus Kx. So this guy, it keeps on changing. So we can't say a constant force is applied at blah, blah, blah. No, we can't say that. So it keeps on changing. So what we should do is integrate it with respect to displacement. So you can put in values, whatever the values we want here. For example, xi equals to 2, xf equals to 5. And you integrate this equation with respect to your displacement. So this becomes 5, 2 minus kx dx. So this is the work done by the spring. If they ask you, what is the work done by you, by F applied? So this equation becomes 5, 2 kx dx. Okay? So sometimes you see there's a negative, sometimes you see there's a positive. It simply means one is elastic force, one is F applied. Okay? I think you've learned this in SPM yang F equals to Kx. For sure. Ada tak belajar dulu?
Ada.
Ada kan? But you only learned the positive one, right?
Yeah.
Okay. Any questions for me? Is everyone okay with the spring? Any questions about the spring? On how it's alive?
Doctor, that means elastic force is always negative, is it?
Yes, if your displacement is negative, then your force is in the positive direction. Betul tak? Displacement ada direction. Kalau kita punya displacement positive, okay, let's see. If our displacement is positive, then yes, our F is negative. If our displacement is negative, boleh kan? Kita punya displacement kan ada direction kan? So this guy becomes a positive. Sorry, F pada. This is positive. This is negative. What that means is F is going this way and positive F is going right. Tu je. But the magnitude is still the same. So that is why people just use F equals to Kx. Sebab sama je, value dia sama. But now that we are learning about vectors, we need to know the direction. So now it becomes important. Okay. Is that okay? Sorry lah, huru hara pula. Tak plan betul spring ni. Okay, so I'm gonna move on to the next slide if you guys are okay. Okay, so tadi kita tengok force that is varying. So what happens? We need to integrate it. So last time we talked about work done if the force is constant. So the equation is, siapa yang asyik masuk tu? F dot displacement, right? Or delta X, boleh. But this is for constant force. When the force is varying, this is your equation. Okay, so there are two different equations for work done and you should be aware of this. Varying force, constant force. Okay. This one is okay. Okay, so there's another varying force, electrostatic force between two charges. Kenapa ada save pula ni? Okay, so this guy keeps on changing with respect to radius. R is radius between charge Q1 and Q2. Okay, so this is another interesting equation. You will learn this more on this in next semester. But for this chapter, you will know how to find work done for this type of force. Okay, so when you integrate this, this becomes a negative, right? Because this guy becomes 1. But actually, it's actually r to the minus 1. So that is how you get this minus. So this is your final equation after you integrate it. And then put in the values, put in the values. For example, R1 is 5, R2 is 10. So just plug in the values, you will get your work done. Okay, kena tahu integration lah basically. Kalau tak tahu, saya tak boleh nak bantu, tu maths. Okay, so graphical representation of work done by a force. Okay, so the important thing to know here is the area under the curve, okay, of a F versus H or X graph. Displacement lah terus. F versus displacement of a F versus displacement graph is work done. Saja nak susahkan diri kan? Nak pakai graph pula, tak apa. So area under the curve of a force versus displacement graph is work done. For example, I say what is the work done between, okay, sekejap, kita buat kosong kat sini, kita buat 10 kat sini. What is the work done between 3 and 7 displacement? 3 and 7 height, contohnya. So you have to calculate the area of this square. So this guy is 5. So macam nak kira square, 3, 7 darab 3, 4. 4 darab 5, 20. So the area is 20. Okay, what are the units? Force is Newton, H is meter. Newton meter, right? So area is 20 Newton meter. This is work done. Is it a positive or a negative? So tadi we learned about if we have, we have force X, we have pushing force, and we have the force by gravity. So it depends on what type of force that is acting. Even though the graph shows a positive value, the question will tell you whether the work done is positive or negative. So it depends whether it's the guy pushing it, or it's the force of gravity, or it's the reaction force. So your work done is positive or negative depending on the question. Your curve or your graph will only give you the magnitude for work. Okay, so this guy is magnitude only. Okay, is this clear?
Clear.
Okay, so this is for a constant force. Force is constant. With increasing height, the force remains at 5. So that is F equals to 5. Walaupun height dia 7 ke, walaupun height dia 3 ke, walaupun height dia 10 ke, 0 ke, F remains 5. So that is when your F is constant. It's a straight line. Kan? But what happens when you have a graph like this? So kalau graph macam ni senang jugalah, because you only have to calculate for the triangle over here and the box. So senang lah. Just calculate that and you get your magnitude for work done. And then you decide whether it's positive or negative depending on the question. For this guy, ni kena pakai integration. But I don't think this will be question on the exam. Only examples like this. So area under the curve gives you magnitude of work done. Positive or negative depends on the question. Depends on which force. Okay, problem solving strategy. Read and understand the question, visualize and sketch the situation. I cannot stress this enough. Sketch, sketch, sketch. Kalau tak sketch, rotan. Always try to sketch your situation, because most of the time mistakes are done when you don't draw it, you can't visualize it, and you make mistakes. And then identify all forces acting on the object. Sketch a free body diagram. We have done this. We always do this. Identify the displacement. Is it to the right? Is it to the left? Is it upward? Is it downward? Just as we identified motion for chapter 3, we need to identify displacement. And then resolve the forces. Where is my pen? Okay, ada. Hilang tadi. Resolve the forces into the x-axis, y-axis. Only consider the parallel components. Resolve. Okay, dah resolve dah lah. Okay, calculate the total work done. Do not forget units, Newton meter or joules. Okay, let's do one example really quickly. Okay, let me copy this into a Word document. And copy. Funny. Bukatlah Word. Degilah semua benda hari ni. Ha, dia pun. Ish. Go. Okay, let's take a look at the question. Sekejap, sekejap. Kenapa dia macam ni? Okay. So a block of mass is pushed. So the mass is 25 kilograms. Okay. Pushed 1.2. Displacement. Yes, we already identified our displacement. Along a frictionless horizontal table. No friction. Horizontal table. Okay, draw the table. Macam biasa, minta maaf atas keburukan gambar. By a constant 36 Newton force directed below the horizontal. So I forgot to draw my box. Baru cakap kena lukis semua benda. Terlupa. Okay, so box. Okay, so and then my force is below the horizontal. So first I draw my horizontal line and then I draw my force. Dia cakap below the horizontal is 35 degrees. That is 35 degrees. Okay, if you decide to draw it this way, is it the same or not? Sama ke tak? Is it the same?
Same.
Same. If it is this way, is it the same or not? 35 juga sini. Is it the same or not?
No.
Why not?
Because it above horizontal.
Because that is above horizontal. Yes. Always try to understand the question. Betul. Good. Okay. So both situations are correct. Let's just go with one, so we are not confused. Okay. Let's use green. So we have, okay, and then we have visualized the situation. Draw the free body diagram. Okay, I'm following instructions now. R, because it is in contact with the table. If it's flying, there shouldn't be any reaction force. I will always have weight because I am on Earth unless you are in some other planet. And then I don't have friction because it's a frictionless table. So even though there's motion, there's no friction. So this is my F. So F, I can extend it like this. Boleh juga. Now keep it here pun boleh. So this is 35. Okay. Boleh je. So this is the diagram. I am just putting all the forces at my center of mass. So that it's easier for me to resolve it. Okay. So now let me redraw that kejap. Really quickly. Oopsie, oops. Come on. Okay. R here. Weight here. F here. So angle is 35 here. So if I were to resolve my F, it will be here, Fx, and it will be here, Fy, upwards. If you can't see this, extend it, do the same thing. So resolving this will give me something here, Fx, something here, Fy. Boleh juga. Let's clean that up. Okay, so now we have our free body diagram, yay. Am I missing anything? Reaction, weight. Okay, I think I got everything. Okay, dia cakap determine the work done by the applied force. So that's easy. So that's simply work done by the applied force. I'm going to label this as work done F applied. Right, so that is F applied dot product with displacement. That is our equation. F applied that is parallel to delta x is F cosine 35, which gives me Fx. Can F cosine 35. times delta x. Okay, that is the parallel component to this, to the displacement. Oh, I forgot to label displacement, but we already know where it is. Kalau saya tolak dari sini, obviously the motion is to the right. Kan ada terbalik pula kan, konon-kononnya. Kita buat positive word lah ni. Okay, did it specify to the right? Tak ada. So if your assumption is the opposite way, you will get negative word done lah, which is also correct because the question wasn't specific enough. But let's just make this easier and say displacement is to the right. Okay, so displacement is to the right and F applied is 36. Cosine is 35. Displacement is 1.2 meter. If this guy is in centimeter, always convert it to meter. Your SI unit is Newton meter or joules. Always, always, always convert to meters. Okay. So this will give me, I don't know, I don't have a calculator. Ada tak nampak calculator saya dalam kelas? I think I lost it. Sedih lah.
35.39.
35.39. Yeah. Okay. Did everyone get this?
Yeah.
Yes.
Everyone try.
Yes.
Yeah, ke? Okay. That is for the work done by applied force. And then the normal force exerted by the table. Kita boleh nak buat, kalau nak terus cakap zero pun boleh because it's perpendicular. See, this guy is perpendicular. So we all, obviously the work done is zero. But tiba-tiba rajin kan, buat je lah. Boleh juga. So F by FR, let's just say R. Confused lah pakai FR. Just say, so, korang kan rajin, so kita buat lah. So this is R. So R dot product with X. So the dot product, we're expanding this equation, F R cosine delta X. The angle between these two guys is 90 degrees. Substituting cosine 90, you still get a zero. Thank you. Okay, next. Let's do the force of gravity, same thing. Displacement is this way, but the angle between these two guys is 90. So work done by force of gravity is also a zero. Yay. That makes my life easier. So, and then it's asking the work done by the net force on the block. So previously we've seen that the equation says work total is F net dot product with delta X, right? We can also say W total is WF applied plus WR plus WG. So this is an easier approach to this. Sometimes it's easier to use this equation. Sometimes it's easier to use this equation. So for this time, this guy is easier, the second one. So because this one is zero, this one is zero. So I am left with 35.39 joules. So that was a pretty easy question, right? Boleh dapat full mark as long as you put in your units. Any question for me? Was that okay? Senang kan? Any questions? Is everyone okay? Still sleepy? Or am I being too hyper today? Are you guys okay? Macam senyap macam hari ni.
Okay.
Yeah.
Okay.
Ngantuk ke?
Tak.
Okay je. Okay.
Yes.
Oh, okay. Okay, so tadi work done. Now we are talking about energy. So you need energy to do work, obviously, right? So the definition of energy is capacity to do work. You need, when work is done, there is a change of energy. Yep. Okay, so Shakila pun rasa penat lepas buat kerja, dia basuh pinggan tadi kan, oh penat. Okay, so there is a decrease in energy. Positive work means that energy is gained. Saya makan, so jadi gemuk, so I'm gaining energy. So, and then Shakila buat kerja, menebang pokok, She's losing energy. So negative work is done on Shakila because she is losing energy. Saya pula work done is positive on me because I'm eating and I'm enjoying it. So I'm gaining energy. Shakila loses energy, negative work done. Right? Senang je lah makan dengan tak makan, buat kerja dengan buat tak kerja. Okay, so definition of energy, capacity to do work, blah, blah, blah. The energy is a scalar quantity. Why? Because it's a dot product, right? Dot product only cares about the magnitude. Energy is a scalar quantity. Oh, sorry, this is work done. Tapi work done punya unit is Newton meter or joules, right? So it's the same unit. Energy is also joules. Both of these are scalar quantity. Okay, so joules ni sebenarnya tak ada direction. You only know if it's positive or negative, and that depends on the situation. Okay, doesn't have an angle lah, basically. Energy can be in many different forms, such as kinetic, gravitational potential energy, elastic potential energy. Yes, question? So these are mechanical energy, moving energy. Moving, Kinetic is moving, gravity, bukan moving sangat lah. Kejap je nak cakap mechanical ni. How do I explain mechanical energy? Sebenarnya moving. But how do I explain this part? Okay, the energy increases or decreases with movement. Okay, contoh Contohnya. Why is it called mechanical? So, I have a ball. Macam biasa. I have a ball and it is previously on ground. So my displacement is x. My displacement is 0. And then my ball, I lift my ball by h. So h is now my displacement of the ball. And gravitational potential energy says that U equals to mgh, where mg is the force, this guy is the displacement. Kan? Mg is weight, gravitational force, and h is your displacement. So with increasing height, your U changes, your gravitational potential energy changes. So when you are moving the ball, there is movement involved, your gravitational potential energy changes. It can decrease or increase. So that is why it's called mechanical. You have to have some kind of movement for the energy to transform or energy to increase or decrease. Same thing with elastic potential energy. You have a spring. Okay, this elastic potential energy is associated with a spring. You need to compress or you need to stretch your spring for the energy to be increased or decreased. Okay, so these three guys are mechanical energy because some type of movement is needed to change the energy. Okay, kinetic energy, I'm sure you know what this is. It's just velocity or just speed of the mass, right? Okay, so kinetic energy, we know the equation is Ke equals to 1/2 mv squared. That is kinetic energy. I think we already learned this in SPM. This guy is mass and this guy is velocity. Always put in your SI unit. Mass is kilogram, V is in meter per second. If it is not in kilogram or not in meter per second, please change it to SI unit before using this equation. Okay? Always use SI units, pakai equation. Okay, so how do we derive kinetic energy from work done? Why do they have the same units, right? Kinetic energy has joules. Work done pun joules. How? So work done is equal to Fs, force times displacement. F is equals to ma, and we know A is from this equation. So just rearranging this whole thing to become V squared minus U squared over 2A equals to 2S equals to A. So I'm just plugging in this guy over here. This gives me 1/2 mv squared minus 1/2 mu squared. So this guy is the final velocity. This guy is the initial velocity. So this gives me final kinetic energy minus initial kinetic energy. Any questions on this one? So this is the change in kinetic energy or work done. Any questions? Semua okay ke? Okay, just senang je, tak ada orang tanya pun. Okay, so work done is the change in kinetic energy. So that is KE final minus KE initial, right? But KE on its own is just 1/2 mv, Allah. It's just 1/2 mv squared. This is not the change in kinetic energy. If the question asks you work done, it means change in kinetic energy, whereby we have 1/2 mv squared minus 1/2 mu squared. Okay, this guy is known as work energy theorem. So if your exam asks you, define the work energy theorem. So you give me this equation, W equals to K final minus K initial. Now, do I know if you know what K is? I wouldn't know if you know it, right? So when you answer this question, W equals to K final minus K initial, where Kf is the final kinetic energy (1/2 mv squared) and Ki is the initial kinetic energy. (1/2 mu squared). Kena define what is K. Kena define equation K for you to get the full mark on definition. If you are not sure how far you should explain, just go above and beyond. Mesti full mark. Okay? So, but if you just give me this, I don't know, oh betul ke dia ni tahu K tu apa? Betul ke dia ni tahu W tu apa? So, I don't know if you know. So, this is why you have to explain what K is, what W is. Tapi W ni dah tahu dah lah kan, work done. Because it's asking you define the work energy theorem. Oh sorry, tak ada work done kat sini. So work done. Kena tulis. Okay. Kalau malas nak explain macam ni, work done. Kinetic final, kinetic energy final pun boleh. Asalkan define. Okay, I'm very flexible. I don't know about other lecturers. Final kinetic energy, boleh. Boleh jawab macam ni. Boleh Asalkan define. If you don't define it, I can't give you marks. Tu je. Okay, and then, okay, speed will increase if work on object is positive and speed will decrease if work on object is negative. Okay, why is that? So speed will increase. Okay, increase in speed. Kita visualize dulu. Increase speed. Kalau increase speed maksudnya my V final is greater than V initial. Betul tak? Sebab as I'm going, kereta saya makin laju. So my final speed is greater than my initial speed. Okay? So if that's the case, if VF is greater than VI, so 1/2 mVF is greater than 1/2 mVI or U, sama je. So if my 1/2 mVF squared is greater than this, so K final minus K initial will give me positive work done. Okay, and then what happens when our speed decreases? V final is less than VI because I'm slowing down. Sometimes my final velocity is 0. Sometimes it's not, it's just slower than the initial. So now my 1/2 mVF squared is less than 1/2 mVI squared. So now when I try to minus K final by K initial kan lagi besar kan? Lagi besar, this guy is smaller. So my work done becomes negative work done. Okay, so I think I'm going to end my class here. Any questions before I turn off the video? Okay, you guys are surprisingly quiet today. I hope everyone is okay.
Because today is Friday.
Because today is Friday. Friday lah kena happy. Tak ke? Lemau dah.
Yes.
Doktor,
Ya, kenapa?
then why the formula for kinetic and potential energy using 1/2 mv square? Not that is for the final kinetic, right?
That is for the final kinetic.
Final kinetic.
Lagi sekali soalan awak.
Tadi kan untuk kinetic and potential energy punya formula KE equal to 1/2 mv square. Lepas tu kan ada lagi satu 1/2 mu.
Oh ya,
Square.
betul. U dengan VI kan sama.
Oh tapi dia guna V square je.
Oh, dalam yang first tadi tu eh. Ni eh.
Ha.
Ni general
Ha.
equation.
Oh, okay,
Ha.
okay, okay.
Tapi kalau kalau kita cari kinetic energy pakai equation ni je, selalunya velocity is constant. Tak ada perubahan. So V, tadi isu lah nak pakai U ke, nak pakai V ke, selalunya constant lah. When we have a change in velocity, so there is work done. So barulah kita concern dengan V dengan U. Baru pakai equation ni.
Oh. So maknanya kalau question tu bagi situation, contoh macam ada benda yang velocity dia increase or decrease, baru kita guna final or initial.
Yes, sebab kan kalau velocity dia constant je, K final sama dengan K initial, betul tak? So work done is 0. So dalam situasi tu we only have kinetic energy but we don't have work done. Okay?
Alright, thank you.
Okay, so work done is always the change in energy. Okay, any other questions for me?
Doktor,
Yeah? Kalau?
velocity constant, work done dia kosong lah?
Betul.
Okay, thank you.
Okay. Tu je. Okay, bye everyone. Have a great day. Don't forget to eat. Have a great weekend. Okay, bye.
Bye. Thank you.
You're welcome.
Thank you,
Welcome. You are welcome.
Bye, doctor.
Bye.
Have a great weekend.
You too.
We are having a busy weekend because of
Kenapa?
FX.
Banyak assignment eh? Oh, proposal. Hehe. Buat betul. Shit.